BayesNets and conditional probability tables. In the previous model, we explained how a causal graph represents a Bayes network, in which the joint probability distribution over the variables is factorized into a product of conditional distributions. Here, we will show how to express those conditional distributions as conditional probability tables. Let's use a simple causal graph relating education, income, and happiness. For this graph, the joint probability distribution is factorized into three conditional distributions: the probability of education, the probability of income given education, and the probability of happiness given education and income. We are going to define the variables in our model as categorical, meaning that we are constraining the variables to take on values in a finite number of categories. For example, consider first the variable education. Assume that education has two categories. If the person has not a college degree, we set the variable to 0. And if the person has a college degree, we set the variable to 1. Now consider the variable income as having two categories. If the person has an annual income above $45,000, we set the variable to 1. If not, set the variable to 0. Finally, define happiness as a variable with two categories. If the person reports that she is happy, set the variable to 1. If not, set the variable to 0. When the variables have two categories, as in our example, we refer to them as binary variables. For clarity, during the next slides, we will indicate, next to the notes in the graph, that the variables are binary, and express the factorization of the joint distribution, so we can follow how this information is used to build the conditional probability tables. In the conditional probability table for a variable, we will express in the columns of the table the values that such variable can take, and in the rows, all the possible combinations of values for all the variables in the conditioning set for this particular variable. Let's start with the first variable in factorization, education. As we can see in the causal graph, education does not have any parent, and thus its conditioning set is the empty set. When a variable does not have any parents, its conditional probability table will only have one row. And as mentioned before, the number of columns will correspond to the number of values that the variable can take. Education is a binary variable. Thus, the table will have two columns. One column for education equal to 0, and one column for education equal to 1. Next, we have to assign probabilities to each of the values that education can take. This is known as instantiate our model. As seen in the table, when education equal to 0, we assign a probability value of p. And given that the sum of the probabilities for all values has to be equal to 1, the probability for education equal to 1 is necessarily 1 minus p. For example, assume that education equal to 0 has a probability of p equal to 0.67. Thus, it necessarily has to be that education equal to 1 has a probability of 1 minus p equal to 0.33. In this case, where there are no variables in the conditioning set, the conditional probability table is known as the marginal probability table. Let's now build the conditional probability table for the variable income. From the causal graph and the factorization of the joint distribution, we can see that income has one parent, education, and thus one variable in the conditioning set. Furthermore, we also know that education and income are both binary variables that can take two values, 0 or 1. First, we determine that the conditional probability table for income has two columns, given that income can take two values, 0 and 1. Next, given that education is the only variable in the conditioning set and education can take two values, the table will have two rows, one for each value education can take. When there is only one variable in the conditioning set, the number of rows will be equal to the number of categories a variable can take. Before assigning probabilities to this table, let's understand how to read its entries. The leftover entry is read as a probability that income has a value of 0, conditioning on education being equal to 0. The right downward entry will be read as a probability that income takes the value of 1, conditioning on education being equal to 1, and so on for the rest of the entries in the table. As mentioned before, each row in a conditional probability table has to sum to 1. So, to instantiate the model, consider the next assignment of probabilities. Finally, let's build a conditional probability table for happiness. This is a more intricate case because happiness have two parts, and thus two variables in its conditioning set. As mentioned before, the number of rows is determined by all the possible combinations of values of all the variables in the conditioning set. In this case, there are two binary variables, education and income. So we have to consider all the possible combinations between the values of the two conditioning variables and assign a row for each of these combinations. So the question is, how many combinations do we have for this case? To compute the number of combinations, we just need to multiply the number of categories of each variable in the conditioning set. In this case, education has two categories, and income has two categories. So 2 times 2 equals 4. We have 4 possible combinations. Thus, we have 4 rows in the conditional probability table. Finally, we instantiate the probabilities and check that each of the 4 rows sum to 1. So, for example, this conditional probability table tells us that the probability that happiness is equal to 1, conditioning on education equal to 1 and income equal to 0, is 0.25.